In this segment, we'll look more closely at how stack frames are created, used, and destroyed. We'll build a detailed word-by-word diagram of the RTS. In the last segment, we talked about the top of stack, but it was a general idea referring to the entire top stack frame. In practice, the top of stack frame is tracked by a designated register pointing to an exact address. In our examples, that would be the address of the byte at the very top of the stack, as indicated here in the diagram. And it will be held in R13, which is a specially designated register, just like R15. R13 is the stack pointer, or SP. In our initial detail diagram, we show SP pointing to the top of the main stack frame. Stack frames are so important that we'll also designate another register, R12, as the frame pointer, or FP. This one will point to a byte at or near the bottom of the TOS stack frame. We'll have a little more detail on exactly which byte in a bit. So that SP and FP bracket the top of stack frame. A second register pointing to the top stack frame may seem redundant, and in some cases we'll use just SP and not FP, or vice versa. But for reasons we'll discuss later, two registers are often useful. And at this point, we should talk about what we mean by up in the runtime stack. Which way in memory is the runtime stack growing when we add a new stack frame? It's growing toward lower addresses. The address in SP decreases as the RTS grows. And the arrow here toward lower addresses shows that. This may seem odd, but it's a common convention, and it makes it natural to draw memory diagrams in which memory addresses increase from top to bottom, and the RTS moves upward from bottom to top in decreasing memory address order. So how do we load and store local variables and parameters? The prior segment explained that we cannot assume that local variables and parameters are at some fixed memory location because we don't know how many stack frames are below the top of stack. So we don't know exactly where in memory the top of stack frame will be. So how do we write load and store instructions to get local data? What we do is use FP or SP as address registers and offset from them into the TOS stack frame. Each local variable and parameter is at a known position within its stack frame. For instance, let's assume in this diagram that FP points to the word 4 bytes just below total in the main stack frame. To load total into, say, F2 or R2, we could write load R2 and then FP, and remembering that up means to lower memory addresses, #-4 like that. Now, that would then load total into R2. The location of the stack frame may vary depending on prior function calls, but FP will always point to its bottom, and thus total will always be loadable by offsetting -4 bytes from FP. All accesses of local state use either SP or FP as address registers and offset from them to get the desired data within the stack frame. So now that we know how FP and SP are used, let's look at some code in prog4.s. We'll start with a call of range sum from main, which is translated into assembly on lines 44 through 47 here. A function call in assembly generally does take several instructions, and it follows a calling convention, and that determines how to pass parameters, set up a stack frame for the called function, and get any return value. There are various methods for passing parameters in assembly, but the simplest is to use designated registers when there are only a few parameters and they are simple values like integers. ARM assembly reserves registers R0 through R3 for parameters. And these registers can also be used for temporary computations between function calls, as our earlier examples have done. But when you call a function, they must contain parameter values. And the function assumes that it may use them as temporary or scratch registers for its own purposes, trashing any data you might have in them. That's why lines 44 and 45 put 10 and 20 into R0 and R1. We're passing 10 and 20 as parameters in the call of range sum. And these two registers will contain the values for parameters low and high. Now line 46 branches to the start of range sum, which is up here. It's like any other branch instruction, but with one added detail. When we call a function, we'll need to return from it, and that will involve jumping back to the next instruction, line 47 in our case. The BL, or branch with link instruction, jumps to the function, but also saves the location of the next instruction in R14, the link register, or LR. And function range sum will use that value to jump back to line 47 when it's done. Okay, so we now have 4 specially designated and named registers. Let's keep track of all of those. We've got the R12 frame pointer, FP, bottom of the stack frame. We've got the stack pointer, R13, and that's the top of the stack frame. We have an R14 link register, or LR, saving a return location, and an R15 program counter, or PC. So let's see. We've got the parameters set up. Now it's the function's job. So after line 46 branches to the start of range sum, lines 4 through 11 will set up the new stack frame for range sum. And setting up a stack frame is generally the job of the function, not of the caller. So at line 4, we can assume that SP points to the top of the stack frame for the existing function, main. FP points to the bottom of the stack frame for main. And LR points to the place to return when we're done. Also, R0 and R1 have the values for low and high. So our jobs are, first, we're going to save a copy of LR so we know where to jump back. We're going to save a copy of the existing FP and then change FP to point to the base of our new stack frame. 3, we're going to set up space for the parameters low and high and the local variable sum, which I realized I should have shown in there. And once we have space for them, we'll put initial values into the low, high, and sum locations. So let's see how lines 4 through 11 accomplish this. First of all, line 4 saves LR, this is a store of LR, at a location 4 bytes above, 4 bytes lower in memory than the top of the existing main stack frame. This is the first entry in our new stack frame. And it leaves SP pointing to the new entry. Because of the bang, of course. Line 5 does the same thing for the existing FP value. Now we have 2 words in the stack frame. And again, SP points to the top of it. Line 6 changes FP to point to the old FP value in the new stack frame. For the moment, SP and FP point to the same place. But line 7 reduces SP by 3 full words, 12 bytes, effectively adding 3 words of space to the stack frame. And I'll remove the needless PC pointer at this point. Now we have FP pointing almost to the bottom of the stack frame, right there. And we have space for local variables and parameters above it. That's what those 3 words are going to be about. Those are lower in memory, of course. We're going to find that sum is immediately above it, and then next is low and then high. But let's look at the code to determine that. So lines 8 and 9 are storing R0 and R1 into locations 8 bytes above lower addresses, above FP, and 12 bytes above it. And that shows that that's where we are putting our low and high parameters, since R0 contains low and R1 contains high. As mentioned before, we're using FP as an address register and offsetting from it. Now, lines 10 and 11 store a 0 into R3 and then again use address register to store that 0 at the location just above FP, which indicates that that's where sum is being stored in the stack frame, since the C code initializes sum to 0. Okay, so now we have a completed stack frame. Note that the bottom of the frame has information that we need when we return from the function. That's the return location and also the old frame pointer. And the top of the frame holds the local state, parameters, and local variables, just one in this case. Now the code that follows will use FP bracket -4 for sum, FP bracket -8 for low, and FP bracket -12 for high. All local state is maintained via offset from FP. So no matter where the stack frame actually is in memory, we'll get the right locations as long as FP is pointing to the bottom of the frame. Brief question 1 here. Revise lines 8 through 11 so that they make no use of FP, instead using just SP. If you think about it, what we really need to do is change FP -8 to FP +4. -8, value of low, is the same as SP +4. Remembering again that lower addresses are in the upward direction. And we replace, of course, FP -12 with just SP. And we replace FP -4 with SP 8. So we can access the frame either way. The next segment will cover the remainder of range sum, including the process of undoing the stack frame and returning.